Thank you.
All right. Well, as I was saying, Joyce, thanks very much for giving me another opportunity to present here. I really enjoy these events. It's all the talks are interesting and they're really well organized, and it's nice to see you again and some of the people from last year. So the plan is to present some work in relation to legal decision making, and what makes legal decision making interesting, unlike sort of general decision making, is that in legal decision making we have a higher expectation that people ought to behave in a rational way. So I'm going to start with some findings from our work, which show some apparent contradictions with rational expectation. I'll have to explain what constitutes rational expectation here, and then offer some insights for how quantum cognition might help. We do have a quantum cognition mailing list. So if you'd like to join this, please just drop me an email and I'll just add you up. It's a little bit quiet right now, but we've only put it together recently. The idea is that we circulate in that list sort of announcements and new work from this kind of research program. All right, so I don't know whether this gets in the way or not. Let's reduce it so that we have. So first of all, let me present you with this task. James Yeasley put together the task, and it concerns a hypothetical suspect, Smith, who is accused of murdering Dixon. So Smith and Dixon had shared an apartment for 9 months. Dixon was found. Dixon was found dead in his bed, and there was a bottle of liquor and a half-filled glass on his bedside table. Now, the autopsy revealed that Dixon died from an overdose of sleeping pills. Apparently, it looks like he took the pills between midnight and 2 a.m. Prosecution claims that Smith slipped the pills into the glass Dixon was drinking. The defense claims that Dixon just committed suicide. And we organized these a whole bunch of statements. So obviously, in a case of legal proceedings, the default assumption is that the suspect is innocent until proven guilty. And we organized a series of statements about Dixon in terms of in groups, such that within each group, the average strength of each statement is equal. Now, I'm not going to go through all of them. The point is, all of these statements are individually slightly weakly incriminating. That is, they incriminate the suspect, Smith, but any individual one of the statements only offers weak evidence that Smith is guilty. For example, Smith had a previous conviction for assault. Well, I mean, all right, by itself, perhaps very slightly indicates that Smith is guilty, but not strongly so. But of course, the point is, if you put all these 12 statements together, you have an overwhelming case that Smith is guilty. So within each block, the statements were randomized, and all participants saw all 12 pieces of evidence. Now, in William's talk, one of the questions in the chat, I think by Zrinka Stimac, was about the observer effect. And in a way, this is exactly about the observer effect. So let me just kind of go through a few more details. So Smith is initially innocent. How should a rational juror determine verdict? And of course, the intuition we all have is that this should be determined by the accumulative weight of the evidence. Now, the thing we manipulated is the number of intermediate judgments that were requested of participants. So participants would see all pieces of evidence. They would know there'd be more evidence to come, right? But at various intervals in sort of between participants' conditions, participants would be asked to make an intermediate judgment. This was highlighted as an intermediate judgment. So for example, in the case of intermediate judgment, after, say, each question, participants would be asked, well, at this point in the proceedings, in case of what you've seen so far, do you think Smith is innocent or guilty? So it's like a case of having exactly the same number of pieces of evidence and just manipulating the density of these intermediate judgments. Final judgment was always requested. And the question we asked is whether the final judgment depends on the density of intermediate judgments. Again, rationally, without having defined what rational means right now, we expect this final judgment to really depend on these intermediate judgments, because from a sort of intuitive expectation for rationality, well, it's about weight of evidence, not intermediate judgments. And basically, we found behavioral evidence for what one might label an effect of a watched pot never boils. I'll just kind of highlight just a handful of aspects of this graph. So these are the number of intermediate judgments, right? So remember, each participant saw exactly the same number of evidence. And this is the probability of no change of initial judgment. This is called the survival probability. So the higher this probability, the more participants do not change their initial judgment. In all cases, this initial judgment was that Smith is innocent. So that the higher this probability, the more likely it is that the final judgment would be that Smith is still innocent. Now remember, this is after exactly the same number of 12 pieces of evidence. And you can basically see that as the number of intermediate judgments increases, the survival probability increases as well. Doesn't increase fully monotonically, because there are some other issues here which I can explain. But broadly speaking, this is a quantum Zinn effect. Well, just say Zinn effect for the time being. It's a Zinn effect in the sense that the more you measure, the more you slow down change. And here you got something similar. Again, there is a non-monotonicity here, which I can tell you about if you want. But the key result is this trend over there. That is that with more intermediate judgments, the survival probability increases. So such a finding challenges rational expectation. I sort of not really said very much about what rational expectation is. I mean, we'll talk a little bit later about this. It's basically Bayesian theory. It's kind of, on the whole, it is more or less uncontroversial that if we think of what we expect in relation to rational decision making, this is matched to Bayesian theory. Now, understand, not all of you would know what Bayesian theory is about. I'll talk about this later. But in any case, it's the idea that probabilities sort of exist about events without our decisions affecting these probabilities. Now, in this case, we have a situation where intermediate decisions basically affect our probability judgment. That is a non-Bayesian effect, and it is not rational according to Bayesian theory. All right, so let me show you a second example, which is a kind of classic whodunit case. So participants were told about John and Jane, a sort of reasonably wealthy couple. In their home, some jewelry goes missing. The 9 suspects, including somebody who was initially presented as the likely suspect, and John and Jane's son, Chad, who obviously, initially at least, would not really be a suspect. So the story makes the local shady character initially suspect. There is new information that Chad needed money to repair a wrecked car. So, of course, that makes Chad the suspect. Now, what's special about a scenario like this? Why is it significant? Well, because it concerns probability updating, right? And Bayesian theory, again, has some constraints about how probability should update from some initial priors to some posteriors. So prior probabilities are the probabilities we have about an event initially, in the absence of any sort of new evidence. They're not true priors. Everything is posterior to some priors. But anyway, like in case of this, in the case of a problem like this, then the priors are the initial probabilities for whether the shady character is guilty and whether Chad is guilty. And then participants see some evidence. And the probability updating is the calculation which tells us how new probabilities are computed. Now, probability updating is at the heart of human reasoning. We do this all the time. We have some ideas about the world or about events in the world. We receive some information, and then we update these probabilities, these beliefs. The key point is that in Bayesian theory, there is the rule for updating probabilities, Bayes' rule, constrains how much you can jump from priors to posteriors. You can't just do this in very large jumps. You're constrained to do it in jumps of only a certain size. In fact, famously, the first instance of pointing out that the Bayesian probability updating is constrained goes back to the 17th century, when Oliver Cromwell apparently said to the members of the Synod of the Church of Scotland to think it possible that you may be mistaken. So how this comment relates to Bayesian updating is that if you have a zero probability for any particular belief, then according to Bayesian theory, it's impossible to update from zero to any non-zero probability. So what Cromwell said basically is, well, don't assign a probability of 0 to anything, because this means you can never update from a zero probability. That's called Cromwell's paradox. So this is Bayes' law. It's arguably the most famous law in decision making. It says that the probability of the hypothesis given some data is the probability of the data given the hypothesis times the probability of the hypothesis divided by the probability of the data. Now, posteriors, this is a posterior probability, depend linearly on the priors. These are the priors over here. So that's the point. That's the tricky bit about Bayesian probability theory. So when the priors are 0, when this term over here is 0, the posteriors have to be 0 too. That's it. That's Cromwell's rule, or in some work with Irina Bassieva, we called it the zero priors trap. You know, once you assign a zero probability to anything, you're trapped to this zero probability. You can't go beyond it. So, all right. So, I mean, it will surprise no one to hear that the initial probability that Chad was guilty was very, very low, but the posterior was very, very high. And Bayesian updating cannot capture these results. So let me now tell you about a third set of results. And here I'll start introducing in a little bit more detail the idea of what Bayesian rationality is about and how it could be, how it could relate to this quantum theory you keep hearing about. Now, if you're a prosecutor or an attorney, you might think that you'd save the most important piece of information for last. For example, to maximize impact. You might feel that the order of presenting evidence could be manipulated to have greater impact with some jury. Or you might think that some intermediate judgments could be manipulated as well. You might think that, well, if I keep, if at a sort of critical point in the proceedings, I urge the jurors to think about whether a suspect is guilty or innocent, maybe this will help my case. This will affect their beliefs. Now, all this, if sort of from a general decision-making perspective, a behavioral economics perspective, all these would be called heuristics or biases, right? They're not rational in the intuitive sense, because the intuitive sense of rationality is that, again, the probability of guilt or innocence should depend on the weight of evidence, not on order and or on intermediate judgments. Of course, it's well known that order effects exist in decision making. Joyce has done some very well known work on this, as well as many others. And it's also generally known that intermediate judgments can impact on belief states. Now, how does all this come together in the case of legal proceedings? Now, let me just give you some background of research outside, not necessarily in relation to any model, just to motivate the idea that, well, at least I mean, there is some good evidence that there are order effects. So a lot of investigators have been reporting recency effects. That is, that if you have a series of pieces of information relating to a legal case, then there's a recency effect. The one you present last tends to be better weighted. And some people have argued, well, this is plausible because of better memorability. You know, you're more likely to remember the thing that was presented last. But of course, others have also reported primacy effects, that is, effects whereby the item presented first is better remembered and seems to be more weighted. And of course, it gets more complicated. I mean, there is a quite sizable literature of biases like this. And in fact, it's hard to come up with a coherent conclusion. Pennington Hastie suggested, well, that it's not really about recency effects or primacy effects. Rather, what matters is whether some evidence is arranged in a narrative. And when this happens, you have a stronger conclusion, regardless of primacy or recency. And Charman talked about context effects. So, for example, a context effect would be, well, if you can't assume that the person is guilty, you'll selectively interpret evidence for guilt in relation to evidence for innocence. So, it's the broader context of some information impacts on how it gets evaluated. Now, none of this would surprise you. I mean, sometimes psychology is criticized as being a science of just stating the obvious. The thing, I suppose, that's kind of may lead us to pause a little bit and take stock is the sort of the diversity of the results. That is, well, some people talk about recency, some about primacy, some talk about narratives or context, and all of these individually seem plausible, they seem reasonable. It's just hard to achieve an integration between them. And of course, sometimes there are no order effects. In a very famous study, Berkus et al. Reported recency effects with family physicians reasoning about the medical diagnosis problem. So picture this: we're talking about people who are actually basically doctors, right? So imagine your local doctor. You go to them with say 2 pieces of information, a lab test and some symptom. And depending on the order in which these 2 pieces of information get processed, the probability that you have a disease or not was different by a sizable amount, by about 5-6 percentile points. And I mean, that's kind of interesting. It's a little bit disturbing as well, because, in cases like medical diagnosis, you expect consistency, right? You expect, again, as in legal cases, you expect the weight of evidence to determine the probability of a disease, not incidental factors like order effects. But then again, these researchers could not replicate, and they offered various reasons as to why they did not. But again, I suppose that's what I want to sort of illustrate, is that there are a lot of kind of very visible results, like this Berkus et al. Result, that don't always replicate. And one kind of wonders, well, is there a problem with the finding? Are the methods differences, or what is going on? We also have evaluation biases, that is, a bias relating to making a judgment as opposed to just observing. Now, we've already saw that in that Zinn effect results I showed you, whether people just observe some piece of information or are asked to make some judgments in relation to this piece of information seems to impact on the final judgment they make. For example, Charman and al. That kind of relates to this context ideas. A prior conviction of guilt would reduce evidence consideration. People would just assume the person is already guilty, and this will sort of color the way they perceive any evidence. There are sort of various kind of other insights like this. Hogarth and Einhorn had a very sort of extensive review of such order effects, and they argued that step by step increases recency. That is, if you make an intermediate judgment after each step, you increase the recency effect. That is, the weight of the last piece of information increases. compared to making a wait till the end judgment. They didn't just review legal decision making. There's a more general review. Pennington and Hastie talked about wait till the end would increase confidence compared to an item by item. Again, sort of intuitive ideas, but how can we sort of bring them together? The kind of theoretical ideas that have been proposed are what you'd expect. Some researchers have argued that it's about memory, or their effects are down to memory. That is, when you have something more recently presented, there is better memory, and this is where these recency effects come from. Various others said that talk about asymmetric skepticism. That is, if you believe for whatever reason a suspect is guilty, then you will interpret corresponding piece of information in a certain way. That is, a piece of information that shows guilt would be associated with higher confidence than otherwise. It's a normal bias. It's not something that's not intuitive. The challenge is how to bring these things together. And of course, in social psychology, there are a lot of ideas of this kind. For example, Schwartz famously kind of argued that earlier questions activate unique thoughts or perspectives, which influence later ones. Now, the main sort of interest in legal decision making is that or medical decision making for that matter, is that when we talk about everyday decision making, we're quite happy to put up with a wide range of such biases. Now, if people are reasoning about an everyday problem of low significance and low consequence, it doesn't really matter if there are, say, order effects or an evaluation bias. For legal decision making, we have high expectations. We expect for jurors, judges to be as unbiased as possible. Attorneys and prosecutors, well, I suppose we understand that maybe they try to use tricks in order to achieve a certain effect. But at the same time, at least for jurors and judges, we expect decision-making to reflect as much rationality as possible. Now, Bayesian theory is the generally accepted standard for rational decision-making. Nobody really contests that. The difficulty is, so first of all, let me just point out that Bayesian theory, so we don't need to go into the details of what Bayesian theory is about exactly, but it suffices to say that Bayesian theory is not by default consistent with order effects or evaluation biases or any of these other heuristics, most of these other heuristics. Now, there is the sort of like keyword here, default, which can be a little bit difficult to unpack. Let me just kind of show you really briefly how the lack of order effects arises in Bayesian theory, because it's really straightforward. So, say the probability to answer A to a question yes, and then yes to a question B following A, well, to the probability of A times probability of B given A, right? Now, if you multiply these two things, then that's the probability of the conjunction of A and B. But conjunction is commutative, order does not matter. So you can flip that and say, well, that's the same as probability of yes to B, and then probability to A given B. That is, baseline Bayesian theory doesn't really tell us anything about order effects. Now, it doesn't tell us very much about evaluation biases as well. Now, Bayesian theory, of course, is a theory of probability, right? It's a theory of uncertainty. So let's say you have an uncertain state about a suspect. Let's say you think the person is thinking that the suspect is guilty with a 65% probability, and the probability that the person is innocent is 35%. Now, that state reflects uncertainty. But if I query the state, if I ask this observer to tell me, well, all right, so do you think the person is guilty or innocent? And they say, well, if I have to toss a coin, I'll probably say guilty. There's no requirement from Bayesian theory that this state will change. So that's sort of like the key assumption in baseline Bayesian theory. Now, what's important about a lot of the existing legal decision-making work is that it involves lay participants. That is, excuse me, participants are given a task and they're asked to imagine they're jurors, and then they evaluate evidence or situations like the ones I sort of very briefly outlined. This is not an invalid approach, because common law countries like the USA and the UK, well, it's jurors from the lay public who produce the verdicts. So how, I suppose, a lay individual, if there's an individual with no legal background, makes this judgment is not relevant. It's quite pertinent, in fact. But of course, in such experiments, legal case material is often simplified. And in fact, some researchers have argued that these simplified legal proceedings aren't really psychologically valid. So with Lee White, a long-time collaborator of mine, and Bartosz Wojciechowski. So Bartosz is a solicitor as well as psychology, which is our lag, because he was able to produce for us materials based on actual criminal cases from various district courts and appellate courts in Poland. So we produced some. So the materials for this study it was actually proper legal cases, and or at least summaries of legal cases. But so there was quite an elaborate procedure of how Bartosz selected these particular cases we used. So he reviewed quite a few possibilities. He cherry-picked a couple of them, and then from the smaller subset, he picked up an even smaller subset based on how well the summaries reflected real verdicts. So Bartosz himself rated the cases, and another individual with legal background evaluated them. So the design, so we wanted to look for order effects and then evaluation bias. And the design was evidence order. So each case was divided into two parts, a part corresponding to guilt and a part corresponding to innocence. And you could either have the two parts present in a guilt-innocent order or an innocent-guilty order. So evidence order was one factor. Rating condition was another factor. So sometimes, participants would always be asked to evaluate both pieces of information at the end. Or sometimes they would ask to make an intermediate judgment, and they knew that was an intermediate judgment. But most importantly, Bartosz was able to recruit a sample of 40 lay participants, 20 attorneys, 20 prosecutors, and really impressively, 40 judges. So that's, I mean, that, you know, I mean, when Bartosz came to us with this sample, we just could not believe it, basically. So it's a unique opportunity to have to be able to study these legal decision biases with individuals who represent in many people's minds what should be the ultimate standard in rational decision making. So I mean, the samples were broadly matched, and these are the results. Now, before I present the results to you, a reviewer of our work, who's a professor of law and psychology, basically told us, and I mean, she's right. She told us that, well, what this research shows is something that we knew all along. Judges are human too. So on the whole, we could not identify an interaction by role, but I'll go through results by role in a second, and I'll tell you some impressions. So there's a strong recency effect. That is, whether the last piece of information is that of indicating innocence or guilt, the probability of guilt changes quite dramatically. So this is the probability of guilt when the last piece of evidence is guilty, and it's quite high, much higher than when the last piece of evidence is innocent. So of course, this only applies to when you have two parts of opposite valence. And we think, in part, that's what leads to inconsistencies in the literature. But in such cases, the result seems pretty clear. Now, you can see this effect broken down by role. And essentially, the pattern is identical with the average pattern. So, I mean, if you squint hard enough, maybe you'll think that in some cases there's less of a bias than in others, but the interaction was not significant. Now, this is about the evaluation bias. So before I tell you about this result, let me offer, in full disclosure, a qualification. It looks like there is an interaction. We're not 100% confident that it's reliable because the analysis for this interaction involves a mixed effects model, which with a participant as random effect. Arguably, one should include a case as a random effect as well. So if you include both random effects, it kind of looks like the interaction goes away. Just with participant, it stays. The trouble we have in evaluating these models is that it's a very partial design. So each participant evaluated the 6 cases in only one order and in only one condition between a single and double rating. And the reason why we had to do this is because we want to reduce memorability between cases. So, that kind of looks like an interaction, but, just bear in mind, our confidence is not 100% there that it's a real interaction. In any case, we are trying to replicate this now with a sort of slightly larger sample just to put our minds to rest. Right, so in any case, let's assume there might be an interaction, let's put it this way, and let me show you how to read this graph. Let's look at single rating conditions. So this is the red line. So when the last piece of information is innocent, you get a probability of guilt, which is fairly low. When the last piece of information is guilt, you get a probability of guilt, which is a bit higher. Remember, that's the recency effect we talked about. Now, let's look at the blue line, right? What you see is that the judgment that is quote unquote intended just becomes more extreme. That is, if the last judgment is innocent, then the person is more innocent with this intermediate judgment. And if the judgment is meant to be guilt, then with this intermediate judgment, the judgment ends up being more extreme guilt. So that's the way to read it. Now, again, looking at this by role graphs, it's tempting to think that the interaction goes away for lay individuals and judges. The people we kind of hope would be more rational, but the interaction is not reliable. There are no models here which show this interaction to be reliable. We have fairly high confidence that there's no interaction here. It's just a trend, which, like all trends in psychology, you take as you want. All right, so that's evaluation bias, and that's order effect. So with as far as we know, with the first study involving judges, we find both order effects and an evaluation bias. And again, to quote again this reviewer of ours, well, it just shows that judges are human too. It does raise a question as to whether these biases should not be present for judges or for jurors, but that's kind of a bigger question. That's kind of like, I suppose, beyond the kind of fairly narrow objective of just trying to identify these biases. All right, so there are a lot of limitations in this work, right? So these were, with the exception of the lay participants, the judges, the attorneys, and the prosecutors, they're all very busy professionals. In many societies, judges are some of the most respected and busy professionals. So the only way we could run the study is we gave them the booklets with the materials, and then we asked them to go through the items in their own time, in their own space. So we don't know exactly what they did. To be fair to us, if they did something completely random, there's absolutely no basis for an order effect or an evaluation bias. In terms of theory, I didn't attempt an integrative review. I just wanted to show that there is a somewhat bewildering range of ideas, and it's very, very difficult to formalize, let alone bring together. For example, ideas like narrative or context, well, they're quite compelling at an intuitive level, but I think anybody who's tried to formalize them, they run into difficulties. These are kind of very, very broad concepts in human thought. So talking about Bayesian theory, right? Bayesian theory, so all right, let's kind of take a step back talk about Bayesian theory a little bit, because that, like I said earlier, that's our kind of basis for what rational behavior is. So why are people not Bayesian? I mean, why can't we do this? If it's meant to be rational, and I reiterate, everybody kind of agrees that's the case. Why can't we do it? The reason is, the reason is that the Bayesian theory by itself is intractably complex. And I mean, you've heard a lot about quantum theory over the last few days. The point about quantum theory is that it's also a framework for probabilistic inference, but it's a banded rational version of Bayesian theory. I'll shortly explain how this is in the simplest way I can possibly can. And believe me, I don't understand this in any more detail because the mathematics can become complicated. But this picture is broadly what summarizes the distinction between full Bayesian rationality that ideally we would all have, but we can't, and the reason why we can't. Now, Bayesian theory suffers from a property called closure, which means that given all the questions you have in your mind, it's always possible to construct, it should be always possible to construct a full joint probability distribution, which constrains all more individual questions. Now, let's think about this in the problem of Brexit, which is when the UK had this enormous and really painful debate as to whether to leave the European Union or not a few years ago. Obviously Brexit is a hugely complex issue, and there'll be a set of questions relating to finance, a set of questions relating to migration, a set of questions relating to whatever you want to make S stand for. And you can think that somebody might be expert within each set of questions. So somebody may have very, very good knowledge of how different finance questions relate to each other. And someone may have very good knowledge of how different, say, immigration questions relate to each other, right? So that's plausible. But if you want to be a full Bayesian, you also need to be able to reason consistently about any combination of questions across categories. So it's not enough to just be sort of, to have a good idea of how these finance questions relate to each other. You also need to know of how each finance question relates to each of the I questions and each of the S questions. And so a Boolean algebra is essentially unachievable for any biological or artificial agent, because our limit, the extent of our questions is absolutely massive. I mean, compare this with animal cognition. So in animal cognition, say if you're say a bird or a squirrel or a mouse or whatever, the range of your questions are limited to, say, predation risks, foraging, mating. That's kind of it, really, right? So, and in fact, biologists, sort of computational biologists, have argued that unless you're Bayesian as an animal regarding your questions, you have a disadvantage in evolution, which makes sense. But in our case, the range of questions we have is absolutely massive. It's impossible. And a lot of people have realized this for a long time. Herbert Simon most eloquently made the point back in the mid-50s, and he got a Nobel Prize for his idea of bound rationality. And that's the difference between basically Bayesian theory and quantum theory. In quantum theory, you have exactly this situation. You have basically Bayesian rules within particular sets of questions, but across sets of questions, non-Bayesian effects arise. And quantum theory essentially is a set of probability rules for how to deal with these cases in going from one set of questions like this to another. So in at least some cases, and I'm choosing my language very carefully here, when people observe what look like biases or paradoxes from a Bayesian perspective, well, some of these can be explained with the rules of quantum theory. And that's essentially the foundation for a lot of this quantum cognition research project. That some of the findings that look like fallacies can be explained using these alternative rules from quantum theory for what happens when you go from one set like this to another set like this. All right, so let me introduce briefly quantum theory, and then, so I know I'm sort of running out of time slightly, but the plan is to introduce quantum theory and then to show you an example just with diagrams, no equations, of how quantum theory could in principle explain some of these results. Now, when I say in principle, I'll qualify it later more. In some cases, we have fully developed quantum cognitive models, in other cases, less so. So in these latter cases, well, we offer an intuition with the understanding that it's not a completely foolproof model. So in quantum theory, well, it's these alternative probability rules. The statement is we might explain some biases, right? I mean, it's very possible there are things that humans do that go beyond either classical theory or quantum theory and require heuristics and biases. It's a key question in our research program to understand the boundary conditions as we go from Bayesian to quantum and from quantum to something else. I mean, you might ask, well, all right, so if you're telling us that we probably need heuristics and biases anyway, why sort of bother with quantum theory in the first place? And the answer there is that, I mean, one answer is that it has generative value, and in fact, Joyce has done some very important work showing an a priori prediction on order effects, which is completely surprising. No one expected it. So that's, I mean, there's this big distinction here between theories that provide a good description of some results and theories that allow you some genuinely surprising new predictions. And quantum theory has kind of been paying its way a little bit in that respect. But another advantage is that it allows us to predict some of these biases together. So, for example, James Yeasley and Jennifer Trueblood showed that conjunction fallacies go hand in hand with order effects. And retrospectively, you might say that makes sense. But up to that point, order effects and conjunction fallacies were considered completely separately. And in fact, people were quite happy to offer explanations for conjunction fallacies quite separate from those for order effects. So in the third example, I showed you with in the work with Bartos and Lee, both order effects and evaluation bias were tested with the same sample materials, but it's a little bit tricky to test for correlations due to the very partial design. So we did some sort of pretty extreme averaging, and it looks like there's a correlation. But again, you sort of want to replicate this before offering it for wider consumption. Okay, so I mean, from the previous talk, one interesting aspect was that the feature of quantum theory William picked as significant is discreteness. Discreteness that actually has never been used in quantum cognitive models. It's an interesting thought. It's interesting to consider how it could be used. The characteristics of quantum theory that most people have employed are basically interference effects. So when you have sequences of questions, classically, you have these conjunctions that I showed you, and that's it. Quantumly, well, interference effects arise. And these have been employed very productively by several researchers, including Joyce, including Jennifer, and Jerome, of course, to model order effects. But also, the state is required to identify the question outcome. So if you're uncertain about something, if you are uncertain about whether, say, a suspect is guilty or innocent, or whether you like this painting or not, if I force you to make a judgment, orthodox quantum theory requires the new mental state to identify with your response. I mean, there is some leeway in that, but not very much. So this is called the Luder's projection postulate. So that's kind of like something to help us with order effects. That's something to help us potentially with evaluation biases. All right, so let me, I'll take 6-7 more minutes to just show you some examples of how to work with quantum models, because I think when people hear quantum, they often think that this is something incredibly mathematical and scary, and it is all these things. But at the same time, at the preliminary level, it's possible to develop the intuition to a fair extent just using simple diagrams. So I want to show you some of these examples, some of these example diagrams, because I think they just make these ideas, which can come across as very, very abstract, quite concrete. So in quantum theory, the way you represent probabilities is using diagrams like this. Now, this is a very simple diagram, the simplest diagram you can possibly have, whereby you have only two possibilities, that somebody is guilty or innocent. And these things are called subspaces. These things are called subspaces. That is, they are the one-dimensional subspaces here, but in bigger overall spaces, they could have more dimensions. And then you have a vector which corresponds to, it's a normalized vector. It corresponds to your system. In psychology applications, this system is usually the belief state of the person, of the participant, for example, making a judgment. And then probabilities are squared lengths of projections. So let's say we have this a participant hears some information, and they end up having a state represented by this psi over here. Now, given the state, we can ask, this person, well, what do you think is the probability that the person is innocent? And it will be the squared length of this projection. It would be quite low. So you can see that the probability in quantum theory is to some extent about vector overlap, which is kind of interesting because in cognitive psychology, vector overlap has been talked about quite a lot. So for example, Stephen Sloman had a fairly well-known model for inductive reasoning based on ideas which look as quantum as they can get without actually using the word quantum. It's quite interesting because Steve, at the time he had no idea about quantum theory, right? But he was sort of naturally led to these vector overlap ideas that look very much like quantum theory. And there are quite a few examples like this. Okay, so that may look a little bit complicated, but I'll explain it a point at a time, and then I'll tell you where this diagram gets a little bit wrong, because these diagrams can be taken, they always have to be taken with a pinch of salt. They're not full models. Now, so this diagram is meant to illustrate an intuition regarding how early judgments can impact on subsequent piece of information. So let's say our state is initially psi, right? So that state is one consistent with mostly guilt, a fair amount of innocence too, right? Now let's say I get some ambiguous evidence. Then the probability of of innocence given this ambiguous evidence is essentially following this projection sequence, taking us from psi to ambiguous evidence down to innocence. That's not quite 100% right because that's a conjunction rather than a conditional probability, but it was easier to draw things like this. And if you draw it as conditional probability, it's exactly the same thing. And if you're interested in that, just email me. But like this diagram I thought was a little bit simpler, and the subtlety between conjunctions and conditionals was probably less relevant to the demonstration. Now, let's say instead now that you make an early tentative judgment that the suspect is guilty, right? So from here, you go to guilt. And now from guilt, you evaluate the same ambiguous evidence. And now, as you can see, the probability of innocence is a bit reduced. Now, without, again, offering this with a large amount of salt, not a pinch of salt, the point is that the context of a previous judgment colors your interpretation of exactly the same evidence. And while we haven't got a proper model for this kind of effects, we think it relates to some of these ideas which have been presented in the legal decision-making on how exactly contextual effects of this kind could impact on the way the same evidence is assessed. Again, that's a bit complicated, but just go with me. We've got a mental state called psi, right? There are two pieces of evidence, and we're very, so I had to do this with conditionals because it's too much of an approximation otherwise. We're evaluating the probability that somebody is innocent given evidence 1, then 2, versus somebody's innocent given evidence 2, then 1. So we're here, that's a state, right? We start from the state under all circumstances. So what happens when we look at evidence 1 and then 2, and then make a judgment? Well, we go to evidence 1, then 2, because we're looking at conditional probabilities, we normalize, so that means we go all the way down to innocence. But if we evaluate evidence the other way, we go from evidence from evidence, we are start from our mental state, we go to evidence 2, then to evidence 1, then we normalize, and then we evaluate. So again, that is more correct than the previous diagram, and it shows that quite sizable order effects can arise quite naturally. Now, of course, you'll observe that this cannot be a full model of anything, because in 2 dimensions like this, you have extreme loss of memory. That is, the only thing that matters is the last piece of evidence, whether it's evidence 2 or evidence 1. And of course, that can't be right. I mean, imagine you could have like a million pieces of evidence, which are very, very strong towards guilt, and then the last piece of evidence indicates innocence. If you take this approach too seriously, which you should not, you predict that the last piece of evidence kind of like trumps all the previous ones. I mean, there are ways to get around this issue, but they're technically complicated, and it's kind of like work in progress within this community. I mean, people who do model order effects, like Jennifer and Jerome, for example, in legal decision making, they use slightly different approaches. The thing primarily I want to show you here is that you can have some semi-plausible order effects quite naturally from quantum theory, whereas in Bayesian theory, you can get order effects, but very, very unnaturally. I can expand on this, as much as you want, but just please bear in mind this is a very, very partial picture of quite a complicated situation. All right. So just maybe one more minute to talk about the evaluation bias. So let's say we start with hold on, my computer seems to have slightly frozen. But let's say we start from where you are in psi G, which is a state assuming that the participant is initially guilty. And then you receive some evidence that the person is innocent. Now, you rotate from psi G to psi G prime, and then you're asked to make a judgment, and that's your probability of innocence, which is not very high. But let's say instead you first ask to make an intermediate rating. So from here you go to there, right? So that's your initial belief state. Because remember, when you make a judgment, your state has to change. You make the same rotation, but then now you move a little bit closer to the innocence ray. And the second measurement with an intermediate rating shows you that the participant is more innocent. Now that is, remember, the evaluation bias that Lee and Bartos and I have been trying to demonstrate with legal decision making. It's basically a bias whereby the intermediate judgment makes the second judgment more extreme to what would have been otherwise. Now that's kind of a little bit of a more complete model, because there are good reasons why this ought to be here, or at least there is some justification. There is some justification about the fact that these rotations are the same, and there is some justification as to why the rotation is in this way. So we spent a lot of time trying to just work through these details. We have a bit more confidence that this caricature is slightly, the pinch of salt that's required is slightly smaller than the pinch of salt in the previous cases. So we actually have a model for that. It produces reasonable fits, and it kind of matches well the evaluation bias. Okay, so let me summarize. We showed several examples of biases in decision making. We think it's notable that some of these biases can be observed with with judges, with actual judges, and realistic materials based on legal cases. Making sense of the range of such biases can be bewildering, and we think that the application of formal theory can help a bit. Quantum theory is a good starting point. Bayesian theory helps us evaluate whether something is rational or not. Quantum theory can be seen as a bounded rational version of Bayesian theory. So it's because we can never be fully Bayesian. We have to ask, well, okay, what does the mind do to compensate for that? And we think quantum theory is part of the answer. But of course, quantum theory is unlikely to be the whole story. I think a plausible way to think about the hierarchy of sort of theories that at the bottom you have the foundation, you have Bayesian theory, right? Then you have some formal probability theory, including quantum theory. There are a handful of other candidates, and then basically you have the Wild West. You have principles like heuristics and biases, which are isolated. They can't seem to fit well together, but still they seem to capture something essential about human behavior, which is beyond the scope of formal theories. All right, I think that's a good time to stop. So thank you very much for your attention. And yeah, happy with any questions you might have.
Okay, great. Thank you very much, Emmanuel, for the very interesting new evidence and new testing. And exactly something we have been talking maybe over days is that the theory should be able to falsifiable in certain context, and we know where it applies, where it doesn't. It's not we don't start with like it has to be true. It's really something testable. But while we're waiting for people's question to come in, and then panelists ask question there too, maybe I can have a quick follow-up. I think maybe you can summarize for the audience, like where is the quantum in this paradigm you're expecting? You did a formal model developing.
So, I mean, the quantum, I mean, as you well know from your work too, from your own work too, the way quantum gets introduced can have a couple of like different sort of flavors. And researchers who are more mathematical, like Jerome and Jennifer and James Gisley, they create formal models and they fit the data. And of course, this work is extremely valuable and helps inform. I suppose it's the ultimate test of quantum models, right? Unless you have like a fully developed theory, it's extremely difficult to argue for a model. We think there is some value in trying to get predictions based on quantum ideas, which are more qualitative. And the reason for that is that with complex model fitting, once you have like 4 or 5 parameters, sometimes it's a bit hard to see exactly where the quantum intuition is. And also, of course, I've talked about baseline Bayesian theory, but as probably many participants know, the Bayesians have progressed since baseline, since the time of Oliver Cromwell. They've made some advances, right? And a lot of the more recent Bayesian models are quite sophisticated and have very finely tuned processes for dealing with fallacies. So, for example, 2 such models are the probability plus noise model from Costello and Watts, which assumes that we have Bayesian classical probabilities, which are based on some mental simulation, which is error prone. And that's how fallacies arise. And then there's the Bayesian sampler, which assumes again that probabilities are Bayesian and they're based on mental sampling, but this sampling is affected by heavy priors. Now, say if you take the Bayesian sampler and the quantum model for these fallacies, each model has a number of parameters. And I mean, in our comparisons, the quantum formalism comes ahead, but it can be very slightly difficult to disentangle exactly what does the magic. That's inevitable. It's an intrinsic limitation of our field, I think, that because of participant variability and human variability, we rely on a lot of parameters to capture individual differences. And then once you start introducing these parameters, it can become a little hard to disentangle exactly what does the magic in each approach. So in any case, we think there is some value in just looking at these caricature diagrams and trying to say, well, irrespective of a specific model, can I create an intuition which I think might be approximately correct? So you asked where the quantum is, and in all the work I've presented, it's it's at the level of appreciating that quantum theory basically produces order effects, quite trivially, right? And in quantum theory, it produces evaluation effects. So these are not full models, right? With the exception of evaluation bias. But we I suppose anchor ourselves to these intuitions from these very simple diagrams, and we want to produce some results, hopefully some a priori predictions based on the broader intuition. So that's, I mean, so in a way, quantum can enter this type of research in many ways. In some cases, it can be like a broad intuition, like we expect order effects. We expect order effects to co-occur with something else. In other cases, it's kind of fully fledged models. I mean, both serve a purpose. I think both should be done. It's often the case that you can't do both all the time, right? Because fundamentally we are bounded agents as researchers as well, right?
I agree. So the panelist Mike has a hand, but let me follow up this quickly because it's just really follow up this one. So so it's interesting because, for example, for your observing from the four samples, people like the laymen and the judge has this kind of maybe more in the sense. So I think for the other two sides, they have stronger bias towards
Absolutely.
against
Right.
and a bias. I want to share, maybe I feel like maybe that model can be applied here. So actually I worked on something puzzling as this. So we started with this categorization decision interference, like the early experiment inspired by two-slit experiment, which I will maybe discuss later this afternoon. But anyway, this one is one example. We face the same puzzling things. Actually, this also shows why those formal modeling actually was very beneficial because we found only the evidence, what we expected from the quantum prediction from interference, only in the one kind of stimuli, like the bad kind of people, like, bad, like kind of guilty, maybe this kind of stimuli. But then not on the other kind. There's no explanation, I don't know why. And we replicated like 5 or 6 different experiments. It's just so strange. And it's also always very robust for the one kind of stimuli, but not the other. Just one kind of trial is kind of maybe, in your case, maybe like the guilty kind of case. But we are doing a categorization, how that can interfere with the later decision action. So then we developed something much more formal with how does the process flesh out, more mimic, established models out there, like the implement the kind of utility function and everything, traditional what a decision model would have done. And then it's interesting, then by fitting the parameter, we realize actually the quantum part, we theorized how the entanglement with the belief and action entangled in that sense. Actually, it presents in both conditions, not for everyone, but like in both conditions. But just the difference is the classical part that's different. Is the utility function is different from for the good and bad phase, the two tests. So that make you observe the data look very puzzling. But actually the fundamental process, the black box part is as we predicted, is like quantum part presents for both stimuli. So we would never realize that by looking at the data. So that was kind of maybe very interesting experience, like showing actually the formal modeling was very helpful in this.
Of course, I mean, look, I think most people would agree that the objective of science is ultimately to express some intuitions with mathematics, right? That to have predictions and to have precision in your understanding. And yes, indeed.
I wonder it's the same case here because the judge and lay people, they are more or less neutral.
I'll come to that. Yeah. So I mean, we trying to build models as well, which are basically, rather than rely on these quantum tools directly, like projections, for example, etc. They essentially have classical probabilities augmented by interference parameters, for example, and then you can sort of try to switch on or off these parameters. So you can basically localize your quantum effect. You have a specific parameter in the model whose, I suppose, existence tells us about whether there's something quantum going on or not. And yes, you're absolutely right. I mean, like it is. I mean, modeling often kind of reveals insight, which are kind of invisible to the blind eye. In terms of judges and the lay people, please remember it's a trend. I mean, when we looked at these diagrams, our reaction was immediate, like, oh, there's judges and lay people, the people who are meant to be more rational are not biased, whereas attorneys and prosecutors who are exactly in a frame of mind of trying to sort of bias towards outcomes, they are, but it's a non-significant trend. And the difficulty we have in such a study is that we cannot. I mean, our participant sample is basically limited. The sample size is set in stone. We can't get more judges. So yes, I mean, it is extremely tempting to interpret that as a trend, but it's a trend.
Yeah, thank you so much. Then Michael has a question.
Yeah, so beautiful presentation. Thank you. And I really liked the model you presented at the end. And I wondered whether it's possible to substantiate the mechanisms by looking at totally different experimental settings, which is much more controlled, like with, for example, psychophysics, random dot patterns, and where you can really say the evidence has this much percent in this direction, and then and you can play around with the exposition time, and so to really check this idea you have, which is beautiful.
Right. Thanks, Michael. That's a great question. So doing this in psychophysics, has been our objective for a long time. Actually, there is some work employing psychophysical paradigms. So Tim Pleskach with empirical and John Bosmeyer have done a sort of notable study involving confidence over like this moving dot pattern. So there is some work there, but of course, what we have been wanting to do is try to do something like a conjunction fallacy, right, in a psychophysical paradigm, because then once you move into perception, you're not limited to a single judgment or a handful of judgments. You can have like, I don't know, 100 judgments per participant. And then, you can have like response time distributions and all sorts of things. Now, we've been trying to do that. It's not easy. James Yeasley with Prince Kwasi have, so Prince Kwasi was a PhD student of James Yeasley's. He's kind of created a paradigm which is intended to be a psychophysics paradigm for the conjunction fallacy. But currently, this only exists in his thesis. But that's exactly, I mean, we have had exactly the same thoughts, that especially for model fitting, these decision paradigms can be a little bit limiting in terms of like both the fact that you have a limited extent of judgments, and each judgment has so many different variables within them that it could be like that you're looking at by sort of case effect rather than a general bias. So yes, I mean that is something we're trying to accomplish. Maybe next year we'll have the perception and conjunction fallacy results.
Awesome, thank you.
Great. So we have a question from Matthew Youngs. So in your research on decision making, do you employ any notion of compound system as in a physics?
So that's a great question, and that's a very complicated question as well. So I'll give you my best answer, and maybe it's something different that you mean. Now, it all starts with the fact that Luder's law, this idea that when you make a judgment, your belief state has to identify with the outcome of this judgment, right? And I mean that's how orthodox quantum mechanics works. But a lot of people feel this is too strong a requirement, and also the so-called collapse postulate is not really formalized in quantum theory. That is, the actual collapse interaction is a little bit of an unknown. That is a little bit underspecified, which is something quantum theory researchers have been concerned about. So recently, Andrei Krennikov and Masanao Zawa and a handful of others have been experimenting with the so-called instruments approach to measurement in quantum theory. Now, in the instruments approach, you have a separation between the sort of the belief state and the sort of measuring apparatus, so to say, and in a way that's the system and the sort of belief about the system. So there's a separation between system and measuring apparatus. And then with the instruments approach, you can sort of conceptualize the measurement as a unitary interaction, which basically means that you have a lot of flexibility in what is the outcome from the measurement. That is, if I ask you whether you like this painting, right? And then I ask you whether you like another painting, you can have like a compound system about these two judgments, and then you can have your measurement system, and then you can specify a measurement interaction that does all sorts of different things. In one case, for example, you could require that the second measurement correlates with the first one, or you could require that the second measurement anti-correlates with the first one. Now, Andrei Krennikov and Masanao Zawa used this instruments model as a way to try to capture what they called the triple challenge of the responsive replicability effect, order effects, and the QQ equality. Now, I'm going into a little bit more detail here than perhaps is necessary, but it's kind of important context. Order effects I've already talked about. The QQ equality is a constraint on order effects that Joyce and Jerome discovered, and Richard Schifrin. The responsive replicability effect is an insight that if you have a question A, question B, and then question A again, people would actually repeat their answer to A, their earlier answer to A. So if I ask you, do you like this painting? And you say yes, and I'll ask you, well, do you like, I don't know, ice creams? And you say no, and then ask you again, do you like this painting? The responsive replicability effect is the idea that people will offer the same answer. So you can't do this with normal quantum theory. You can do it with instruments. So that's kind of the summary. That's what I suppose motivates this instruments approach to quantum-like modeling. The two qualifications that are necessary here are first, that with the instruments approach, you move away from Luther's postulate to something which is more flexible. Some people worry it's too flexible. That is, there's a slight danger that unless you put some constraint on what the measurement interaction is, you throw the baby with the bathwater, so to say. The second qualification is that the response replicability effect is basically just an intuition. It's what Andrei and Masanao think is plausible about human decision-making, but I believe Joyce and Jerome have some results which challenge the response replicability effect. And indeed, in developmental psychology, the response replicability effect is well known to be violated. Simply put, if you ask like a child a question, right? Say, is this an orange? And you ask it again, actually the child is more likely to reverse their answer because they thought they got the first answer wrong. So there are a lot of qualifications. So just to sum up, you asked about employing compound systems. So that's one answer. That is, you have like the belief state and something that kind of looks like a measuring apparatus. So you have like a composite overall system, and that allows that has been the basis for some researchers to propose an alternative to Luther's postulate for what happens to the belief state after a judgment. And the motivation for doing so is to capture the response replicability effect, the QQ equality, and other effects. So yes, so I mean, maybe that's not exactly what you had in mind, but that's the most relevant thing that's going on right now in quantum cognition.
Thank you. And I think
But
like
maybe you can talk about the response replicability effect. It doesn't always occur, right, in the ABA paradigm.
yeah, so we could discuss that later this afternoon. So exactly, so with the thought experiment by quite a few physicists and challenging those ideas, and I think in the empirical we indeed derive a like ABA paradigm, like whether the second answer to A would disturb, would change or not. It correlates with the A-B correlation. It's kind of we have some simple. This is derived from kind of like uncertainty principle. It's whether if A-B correlation is larger. So in Emmanuel's nice model at the end, it similarly means the person wouldn't move too far away from the A, so the person would still collapse reasonably close to the original answer of A. But then if it's the B disturbs the system much more, move much away from the A, so in the observed data would be the correlation between A, B answer would be small, then the A and the second answer to A would have smaller correlation. So the change would be bigger. So the disturbance would be bigger. So which was supported by empirical data. But we did.
So the ABA effect, the responsible applicability effect should occur if these are sort of classical questions. But like Joyce is saying, there should be disturbance from the intermediate B question if they're incompatible. So that's kind of an interesting question. I think you found
we picked the questions. So to add to that detail, we picked the questions that we have traditionally show all the effects, which means they are incompatible empirically. So we picked question A, B, show all the effects, which is one way to rationalize incompatibility, this concept in the way.
Well, in fact, order effects seems to be so. I mean, a lot of questions we often get is, all right, well, all this is fine. I mean, you just told us some questions are classical, some questions are quantum-like, right? So how do you decide which are which? And order effects is usually the most common way of trying to do that. So I mean, the approach, I think, of most of researchers in that area is that, we have a combination of questions. Some of them are classical, some of them are not. And then it becomes an empirical issue to try to identify which are which and then follow up with your predictions.
Yeah, so kind of like if there's a sequential effect on judge A and judge B, or judge B and A, those kind of different order, it may be like indicating, at least by our thinking, is that indicating the capacity wasn't enough to have a joint probability of the both. So then there is a kind of incompatible measure for measure A and measure B, project on A and B should be sequential. So I guess like exactly as following up the early intuition from Professor Hubbard is that then maybe we definitely can limit the person capacity, make the person exhausted from decision making, and then the person is so that's why I feel compatibility, those concepts so central to physics actually is much more interesting, maybe more is richer in the human decision, right? Because we could manipulate it in some way by manipulating the capacity, by manipulate the demand of the judgment, or like this kind of measurement on the person.
Well, the slight subtlety here is that, I mean, most of us and throughout the history of this research program, people assume questions are either compatible or incompatible. But of course, the interesting challenge is to try to come up with a way to smoothly move from one to the other. That is, we assume that in the absence of familiarity with a set of questions, these questions are quantum-like, right? So order effects can arise, or other fallacies. The classic example here is the conjunction fallacy with for Tversky and Kahneman. Participants are told of this person, Linda, they've never come across her before. They are told to consider whether this Linda is a feminist and a bank teller. Now, that's a brilliant, familiar combination of questions. You don't often get asked to consider whether somebody is a feminist and a bank teller, right? And I suppose our train of thought is that this lack of familiarity is what makes what indicates to us as modelers that these questions are more likely to be quantum-like rather than classical. And in fact, a couple of researchers like Jennifer Trublat and James Giesler have found that as familiarity increases with a set of questions or a task, then human reasoning tends to become more Bayesian. So all these ideas are reasonably well supported. The thing that's missing is a sort of a formal way to understand how we go smoothly from an incompatible representation to a compatible one. And I think some of these problems are quite challenging because they're not really the type of problems physicists address, right? I mean, from the physics point of view, well, some things are incompatible, some things are compatible, right? There's no practice in nature. So they're not problems they've actually really dealt with. And and it's difficult to sort of like fiddle with quantum theory. It's like getting an iPhone and trying to think, oh, I kind of want to change something about, I don't know, the way the screen works. I mean, you can't just open it up and
Capacity.
start fiddling with things. Quantum theory, mathematically speaking, is an immensely complex object. And for us to come in and say, well, we've got a problem, right? How do we go from, say, incompatibility to compatibility smoothly? Well, it's very difficult.
Yeah. So I think this maybe reminded me about something about like we are maybe a way to clarify is that we're not just apply physics to the human phenomena. So how to do, I think each field does have to develop its own theory, but utilize, how to integrate, how to utilize the formalism or conceptual understanding from quantum theory,
Yeah.
for some of us. For me, I think that's necessary. Like, for example, like this example I just mentioned, like there are parts wasn't predicted by physics. I have no way because it doesn't predict a human decision in that kind of situation. Like
Yes, absolutely. But on top, some of the tools and processes we need to model the human mind effectively are just missing in quantum theory, and that creates a lot of a challenge. So, for example, I talked about this in response to Matthew's question. I talked about this instruments formalism by Andre and Massanao earlier. I mean, their paper is basically about 170 equations, and I mean, it's very challenging to even go through it, let alone actually try to produce something like that in the first place. And there are a lot of challenges like this. But I mean, on the bright side of things, we think the program is exciting because it does produce some new findings. And also, in some cases, one can sort of produce intuitions about predictions on the base of simple diagrams. So my favorite example here is this evaluation bias. So it was Lee White, this colleague of mine, who originally said, oh, it's likely this would occur. And Lee is an organizational psychologist. He doesn't have a sort of specific mathematical or physics background. But once you start with these diagrams and you understand them, which is not challenging, you can play around and you can go some way towards perhaps putting down a prediction, which might work out. But it is important to bear in mind that the diagrams are not full models. Their intuitions are best, and there are very strong boundary conditions on their validity. But they can help. They've helped in the past on some occasions.
great, thank you. So have a few minutes if there are urgent questions. Otherwise, so Emmanuel will be able to join us at 1
Yes,
o'clock.
I'll be there, of course. Yeah, I'm looking forward to it.
So can have some, kind of discussion. I think this is very valuable, especially for many of us, on panelists, I'll organize like Professor Alex Wang, Michael Shanaby, and like interesting, this bigger macro level societal phenomena is even more, maybe leads to bigger compound systems and much more levels of analysis. So it's really challenging and interesting to see how we can brainstorm those ideas.